Before the invention of the camera, the only way to preserve a visual record of the world was through human hands. Paintings, drawings, engravings, and sketches were the primary tools used to represent people, places, and events. While skilled artists could produce remarkable works, manual image making had fundamental limitations. It depended entirely on individual talent, interpretation, and time. Two artists drawing the same scene would produce two different results, each shaped by personal perception and technique. This subjectivity posed serious problems beyond art. Governments relied on drawings for maps and architectural plans. Scientists needed accurate depictions of specimens, experiments, and observations. Engineers required precise visual records of machines and structures. In all these fields, human error and interpretation reduced reliability. A drawing could exaggerate, omit, or unintentionally alter details that were critical for understanding. Time was another constraint. Creating detailed images required hours, days, or even months. This made it impossible to record fleeting moments, changing light conditions, or fast-moving subjects. Visual documentation lagged behind reality. The world moved faster than it could be recorded by hand. As societies became more complex during the late 18th and early 19th centuries, these limitations became increasingly visible. There was a growing need for a method that could capture reality directly without translation through human interpretation. The problem was clear. The world needed a way to let nature record itself. The Industrial Revolution accelerated the demand for precision. Factories, machines, bridges, and infrastructure required exact documentation. Engineers needed accurate visual references to replicate designs and diagnose failures. Scientists sought objective records of experiments, astronomical observations, and biological specimens. Written descriptions alone were insufficient. Publishing and education also faced challenges. Books relied heavily on engravings, which were expensive and slow to produce. Each image required an artist, an engraver, and a printing process. Errors introduced at any stage could distort information. As literacy expanded, so did the need for reliable visual material. In administration and law, visual records gained importance. Property boundaries, construction plans, and official documentation required clarity and consistency. A reliable image could serve as evidence in ways that drawings often could not. This growing demand exposed a gap between what society needed and what technology could provide. Optics had already advanced enough to project accurate images using devices like the camera obscura. The missing element was permanence. Images could be seen but not saved. The need for the camera was not driven by art alone. It was driven by science, industry, and administration, all requiring a neutral, repeatable, and accurate method of visual recording. The idea that light itself could create images was not new. The camera obscura, known for centuries, demonstrated that light passing through a small opening could project a detailed image of the outside world onto a surface. Artists used it as a drawing aid, tracing projected scenes to improve accuracy. However, the camera obscura revealed a fundamental limitation. The image disappeared as soon as the light source changed. There was no way to preserve it automatically. The device showed reality but could not retain it. This raised a critical question. If light could create an image, could it also fix one? The answer required chemistry, not just optics. It required a substance that would react to light in a predictable way and retain that reaction permanently. This challenge attracted inventors who thought beyond traditional art. Among them was Joseph Nicéphore Niépce, who approached the problem methodically. He did not seek artistic expression but technical certainty. His goal was to let light alter matter in a lasting way. By treating image making as a physical and chemical process rather than a human skill, Niépce reframed the problem entirely. The camera was no longer just an optical device, it became a recording instrument. When permanent image capture was finally achieved, its importance was not immediately recognized. Early photographic processes were slow, expensive, and technically demanding. Exposure times were long, materials were unstable, and results were difficult to reproduce. Yet the core principle worked. Light could create a lasting image without human interpretation. Over time, improvements reduced exposure times, increased clarity, and simplified processes. Photography began to spread beyond experimentation into practical use. Scientists used it to document experiments. Architects used it to record buildings. Governments adopted it for surveys and identification. Artists explored its expressive potential. The camera transformed how humans related to reality. Events could be recorded as they occurred. Landscapes could be preserved exactly as they appeared. Ordinary people could be documented, not just elites who could afford portraits. The ultimate success of the camera lay in its objectivity. It did not interpret, it recorded. While later technologies refined speed, color, and portability, the foundational idea remained unchanged. Light interacting with a sensitive surface to create a permanent image became one of the most influential technological achievements in human history. Although Niépce did not live to see the full impact of his work, his solution addressed a deep and persistent need to preserve reality itself. The camera did not replace human vision, it extended it across time, making memory physical and permanent. Joseph Nicéphore Niépce was born in 1765 in Chalon-sur-Saône, France, into a family that valued education, public service, and intellectual discipline. His father was a lawyer and a local administrator, a role that placed the household within the educated middle class rather than the artistic elite. This environment exposed Niépce early to structured thinking, written records, and the importance of accuracy, values that later shaped his approach to invention. The period of his childhood coincided with the Enlightenment, when scientific reasoning and empirical observation were increasingly emphasized across Europe. Books, correspondence, and discussion played a central role in educated households. Niépce grew up in a culture that respected method, evidence, and experimentation rather than intuition alone. Unlike artists trained in studios, Niépce's early environment encouraged him to see problems as systems to be analyzed. Nature was not only something to admire, but something to understand and reproduce through physical principles. This perspective would later distinguish him from painters and engravers who approached image-making through interpretation rather than mechanism. His upbringing did not direct him toward photography specifically. Such a field did not yet exist, but it prepared him to think patiently, independently, and analytically. These qualities were essential for a problem that required years of isolated experimentation, without immediate success or recognition. Niépce received a formal education appropriate for his social class, including studies in science, mathematics, and administration. He showed particular interest in physics and chemistry, subjects that were rapidly evolving during his lifetime. Rather than excelling as a specialist in one discipline, Niépce developed a broad technical curiosity. His education did not lead him directly into an academic or artistic profession. Instead, it gave him tools to observe, test, and refine ideas over long periods. He read scientific texts and followed developments in optics, mechanics, and chemical processes. This self-directed learning continued throughout his life. Niépce was not driven by artistic ambition. He did not seek to paint or draw better than others. Instead, he questioned why image-making relied so heavily on skill and interpretation. This question emerged naturally from a scientific mindset. If light behaves according to physical laws, then image formation should be governed by those same laws. His curiosity pushed him toward experimentation rather than theory alone. He preferred testing materials, adjusting variables, and observing outcomes. This approach required patience, especially given the slow pace of chemical reactions and exposure times in early photographic experiments. Education for Niépce was not a phase but a continuous process. He learned by doing, refining his understanding through repeated trials, an approach that defined his later work. Niépce's professional life did not follow a straight path toward invention. He initially worked in administrative roles and later pursued various mechanical and technical projects. Among these were experiments with engines and printing technologies. Some of these ventures achieved limited success, others failed entirely. What unified his efforts was persistence. Niépce did not abandon problems easily. He revisited ideas over years, sometimes decades, refining them incrementally. This long-term focus set him apart from inventors seeking rapid results or commercial success. He worked largely in isolation, without institutional backing or significant financial support. This independence allowed intellectual freedom but also created constraints. Materials were expensive, processes were slow, and results were uncertain. Progress depended on careful management of time and resources. Niépce's invention mindset was methodical rather than visionary. He did not attempt dramatic leaps. Instead, he identified one obstacle at a time and worked systematically to overcome it. In the case of image making, the obstacle was permanence, how to prevent an image from disappearing. This mindset was critical. Photography was not invented in a moment of inspiration, but through years of controlled failure and gradual improvement. Niépce's ability to continue working without external validation was essential to eventual success. Niépce married and maintained a family life that provided stability rather than distraction. His personal responsibilities required balance between experimentation and domestic obligations. Financial pressure was a constant concern, as his inventions did not generate immediate income. Despite these challenges, family life offered structure. It anchored Niépce's routine and allowed him to sustain long-term projects without total isolation. His workspaces were often part of his home environment, blending domestic life with experimentation. Unlike later inventors who sought public recognition, Niépce worked quietly. He documented his experiments carefully, but did not aggressively promote his achievements. This restraint contributed to his limited recognition during his lifetime, but it also protected the integrity of his work. His personal life reinforced patience and discipline. Progress was measured not in public milestones, but in incremental technical improvement. This approach suited a problem as complex as fixing light itself onto a surface. By the time Niépce achieved a permanent photographic image, his character and working habits were firmly established. His childhood environment, education, independent career, and stable personal life converged to make his achievement possible, not suddenly, but inevitably. By the early 19th century, the optical principles behind image projection were already well understood. Devices such as the camera obscura could project a clear and detailed image of the outside world onto an interior surface using a small aperture or lens. Artists had used this tool for generations to improve accuracy in drawing. However, the camera obscura exposed a fundamental limitation. While it could display an image, it could not preserve it. Joseph Nicéphore Niépce recognized that this limitation was not optical but material. The projected image vanished as soon as the light changed. Tracing the image by hand defeated the purpose of mechanical accuracy. If image making was to become objective, the image needed to fix itself automatically. Niépce reframed the challenge as a chemical problem. Light clearly carried information about shape, brightness, and contrast. The question was whether that information could trigger a permanent physical change in a surface. Rather than improving lenses or projection methods, Niépce focused on identifying materials that reacted to light in a stable and controllable way. This shift in thinking was decisive. It moved the problem of photography away from art and toward chemistry and physics. Niépce's goal was not a clearer projection, but a lasting transformation, an image formed by light and retained by matter. Niépce began testing light-sensitive substances through systematic experimentation. Early candidates included silver salts, resins, and various organic compounds. Many materials darkened when exposed to light, but most reactions were unstable. Images faded blurred, or continued reacting after exposure, destroying detail. Progress was slow. Exposure times stretched from hours to days. Small changes in temperature, humidity, or light intensity altered results unpredictably. Niépce recorded these failures carefully, treating each unsuccessful attempt as data rather than defeat. Unlike later photographers, Niépce lacked standardized chemicals or established methods. He worked largely alone, refining processes through trial and observation. Each experiment required patience, as exposure times were long and results uncertain. The absence of immediate feedback made iteration difficult. Through this process, Niépce identified a crucial requirement. The light-sensitive substance must change in proportion to light exposure and then become resistant to further change. Without this stability, permanence was impossible. This phase of his journey was defined not by breakthrough, but by endurance. Niépce's willingness to continue experimenting despite repeated failure distinguished him from many contemporaries who abandoned the problem as impractical. Niépce eventually found promise in bitumen of Judea, a naturally occurring asphalt. Bitumen hardened when exposed to light, becoming insoluble in certain solvents. This property offered precisely what Niépce needed, a material that reacted to light and then stabilized. He coated a metal plate with a thin layer of bitumen and placed it inside a camera obscura. Over many hours of exposure, light hardened the bitumen in brighter areas while shaded areas remained soft. After exposure, Niépce washed the plate with a solvent. The unhardened bitumen dissolved, leaving behind a permanent image formed by light alone. This process, which Niépce called heliography, produced the world's first known permanent photograph. The image, showing a view from a window, was crude by modern standards. Exposure time was extremely long, contrast was limited, and detail was uneven. Yet the achievement was unprecedented. A real scene had been fixed permanently without human drawing. The importance of this moment lies not in visual quality, but in principle. For the first time, light had recorded reality directly onto a surface and remained there. Photography now existed as a concept, even if its future refinement was still distant. Recognizing the potential of his work, Niépce sought collaboration to improve and promote the process. He entered a partnership with Louis Daguerre, an artist and inventor interested in image making. Their agreement aimed to refine heliography and develop a more practical photographic system. The collaboration produced incremental improvements, but also introduced challenges. Daguerre pursued faster exposure times and clearer images, while Niépce remained focused on stability and permanence. Progress was uneven, and technical difficulties persisted. Niépce died in 1833 before photography gained public recognition. After his death, Daguerre continued developing the process, eventually introducing the daguerreotype. Although Niépce's contributions were foundational, public credit shifted largely to Daguerre, whose method was more practical and commercially viable. Despite this, Niépce's role was essential. He solved the core problem of photography, fixing an image created by light. Without heliography, later advances would not have been possible. Niépce's journey to the camera was not marked by acclaim or immediate impact. It was defined by persistence, methodical experimentation, and a clear understanding of the problem at hand. His work transformed image-making from a human skill into a physical process, establishing the foundation upon which all photography was built. At its core, a camera is a controlled optical system designed to manage light. The fundamental principle behind all cameras, early or modern, is that light travels in straight lines. When light from a scene passes through a small opening or a lens, it projects an image onto a surface inside a darkened enclosure. This image appears inverted because light rays cross at the aperture point. Long before photography, this principle was demonstrated by the camera obscura. A simple box or room with a small hole could project an external scene onto an interior wall. Adding a lens improved sharpness and brightness by focusing light more precisely. However, projection alone was not enough. The image existed only temporarily and vanished when lighting conditions changed. Joseph Nicéphore Niépce understood that optics solved only half the problem. A camera needed two essential components. One, an optical system to form an accurate image. Two, a surface capable of recording that image permanently. In Niépce's time, lenses were relatively crude but sufficient for projection. The true technical challenge lay in transforming projected light into a stable physical record. Niépce's key innovation was identifying a material that reacted predictably to light. He discovered that bitumen of Judea, a natural asphalt, hardened when exposed to light and remained soluble where light did not reach. The process began by coating a flat metal plate, often pewter, with a thin layer of bitumen dissolved in a solvent. Once dry, this plate became the image recording surface. When placed inside a camera obscura, light from the scenes struck the bitumen layer. Bright areas of the projected image caused the bitumen to harden. Dark areas remained soft. This reaction was gradual and proportional to light intensity, allowing tonal variation rather than simple black and white contrast. After exposure, the plate was washed with a solvent such as lavender oil or turpentine. The solvent dissolved the unhardened bitumen while leaving the hardened areas intact. The result was a permanent image formed entirely by light-driven chemical change. This step was revolutionary. It demonstrated that light could directly alter matter in a lasting way, transforming photography from theory into reality. Early photographic exposure times were extremely long. Niépce's heliographic images required exposures lasting several hours, sometimes extending across most of a day. This limitation was due to the low sensitivity of bitumen to light and the modest quality of lenses available at the time. Long exposure times restricted subject matter. Only stationary scenes, such as buildings or landscapes, could be recorded. Moving objects disappeared entirely. Shadows shifted during exposure, producing unusual lighting effects in the final image. Despite these constraints, Niépce's method established the essential workflows still used in photography today. 1. Exposure light interacts with a sensitive surface. 2. Development unexposed material is removed or altered. 3. Fixing the image is stabilized against further change, although later processes dramatically reduced exposure time and improved clarity. The sequence remained fundamentally unchanged. Niépce proved that image permanence was achievable, even if refinement was still required. His process also introduced the concept of negative space, areas where material was removed to reveal an image structure. This idea influenced later photographic and printing techniques. Niépce's camera was primitive by modern standards, but its conceptual framework remains intact in every photographic device today. Modern cameras still rely on controlled light entry, image formation through optics, and light-sensitive recording surfaces, whether chemical or digital. Film photography refined Niépce's ideas by using silver-based chemistry to dramatically reduce exposure time and improve image detail. Digital photography replaced chemical reactions with electronic sensors, converting light into electrical signals. Yet the fundamental logic remains the same. Light carries information, and that information can be captured and preserved. Niépce's greatest contribution was not image quality, but proof of principle. He demonstrated that reality could record itself without human interpretation. This shifted image-making from an artistic craft to a technical process. Photography reshaped science, journalism, medicine, history, and personal memory. It allowed moments to be frozen, evidence to be preserved, and truth to be examined visually. None of this would have been possible without Niépce's insistence on permanence. The camera works because light is both a physical force and an information carrier. Niépce was the first to successfully harness that dual nature. His work transformed light into memory and made visual reality durable across time.